Welcome back, everyone. So I'm really excited to continue this lecture series on reinforcement learning. And in this one, I'm going to zoom in specifically on deep RL, deep reinforcement learning, or said another way, reinforcement learning using deep neural networks. Okay? This is one of the most exciting trends both in control theory and in machine learning over the past decade. And there's just a ton of new and exciting results out every month, it seems, on deep reinforcement learning. Just a reminder, this is following roughly a new chapter in the second edition of our data-driven science and engineering book. So I wrote a reinforcement learning chapter to cap off that control theory part. It was also a great excuse for me to learn more about reinforcement learning. So that's something, actually just a meta point for all of you. Trying to explain things to people is always the best way to learn something. And this was really, I took this as an excuse I wanted to learn about reinforcement learning, so I wrote a book chapter and made this video sequence. So I hope you are also enjoying it as much as I am. Okay, so this is such a big field. I am going to touch on the tip of the iceberg of all of the different techniques of deep reinforcement learning. And I actually have another video from a number of months ago, maybe even a year ago, where I talked at a very high level about how you can use deep neural networks and reinforcement learning. And I mostly did this with examples and demonstrations of all the cool stuff you can do. So today I'm going to dig deeper into more of the algorithms and how these different flavors of deep reinforcement learning fit into kind of our classic pictures that we've been developing over the last few lectures. Okay, I'm going to jump right in, and hopefully this one's kind of exciting. All right, so the first type of kind of deep neural network embedded into a reinforcement learner, kind of the simplest thing you can do, is what's called a deep policy network. So your policy function pi is presumably a relatively complex function of the state you find yourself in, S, and the action you're going to take, A. So it's the probability of taking an action given that you're currently in state A. And this is supposed to be optimized to maximize future rewards in your system. Okay? So this policy pi could be pretty complicated. There could be a lot of rules or physics of how you make decisions and actions optimally given the state that you find yourself in. I don't know why I have a terminator here, but presumably it's using a deep neural network to optimize its policy. And so that policy function pi can be parameterized as a neural network with weights theta. So the input of the neural network is the state, the output is some probability of which action to take, and you may flip a coin and take an action based on that probability. And so what we would be trying to do is to optimize over these parameters theta to maximize the future reward, to give myself the best policy pi possible. Okay, so there is a brilliant blog by Andrej Karpathy, Deep Reinforcement Learning Pong from Pixels, where they essentially walk through and they actually provide a Python code with about 150 lines of code that actually codes up this deep policy network. So it's really, really cool. Basically, how you would take a high-dimensional state S. This is a high-dimensional measurement of your system. This is pixel space, so there are over 1,000 pixels in this image that are input into this policy network. And then essentially, the policy network is optimized to make the best decision of whether or not I should move up or down my Pong paddle. Okay, so you're this character on the right, and all that you have to do is, based on the current pixels, decide what's the probability of moving up or down, and then take an action based on that probability. And so the idea here is, at a very, very high level, is that we have our policy parameterized by the network weights theta, and we're going to optimize over theta to give us the best chance of getting a future reward. And I'm being a little bit intentionally vague about, I'm not writing down a loss function, a neural network loss function that we're training over. because there are different ways that you can optimize using these deep policy networks. And actually, one of the easiest ways, essentially, you can use backpropagation. So, neural network training in general uses this idea of backpropagation. So information kind of upstream can be propagated back and eventually used to compute gradients and optimize these weights. And so the basic idea is that I would optimize my weights by computing gradients based on this cumulative expected future reward. And so this is partly why I'm being vague, is you have a lot of choices on how to represent this future reward. So if you represent that cumulative future reward using a value network, so if you have a policy network to make actions, to make decisions on what actions to take, and you are estimating your future reward using a value network, that would be an actor-critic network. So there's different ways of kind of embedding information into this deep policy network. But the basic idea is that you represent your policy as a network, and you optimize over its parameters using essentially gradients gradients of something through backpropagation. I'm going to talk more about this. Okay, this is an aside that I think is really important, and I want to tell you about. But if you don't love, math derivations, you can skip these next 5 minutes. This is kind of the guts of how policy gradient optimization works in general. This is more general than neural networks. If you have a policy function pi that is parameterized by some parameters theta, this could be a support vector machine, this could be some other kind of model, or it could be a neural network where the weights are parameterized by theta, then I am essentially going to derive how, if you take the chain rule, or if you take the gradient of this reward function, this cumulative reward function, you can get a signal to update your policy weights theta. So again, if you don't love math, you can skip this next 5 minutes, but I think this is kind of important. Okay, so the cumulative future reward, R sigma, given a set of parameters theta for my policy, so you can think of theta as being a policy if you like, is the following. So mu sub theta is the kind of expected future distribution or probability of finding yourself in a state S at long times given this policy theta. So it's kind of the asymptotic distribution. If you played this game for a long time, this would be the expected probability of finding yourself in any of those states S out of all possible states. So this is a probability distribution of where you find yourself in long times. This is kind of just to be mathematically precise. We need this part here. And we would add, so we weight by the probability of finding yourself in a state in long time. And then you weight by the quality function, the quality of being in that state, okay, and taking that action, times the probability of taking that action given your weights theta. This is a bit of a complicated expression. You can kind of convince yourself that this is true, and this is outlined in detail in the chapter in the book, that this is consistent with how we normally write this reward function as the sum of all the future possible rewards. This is just folding it up using this quality function. Okay, so it's the quality of being in a state and an action, so I have to add up over all of the probabilities of being in taking any of those actions. So this is a sum or a weighted sum over actions. And similarly, I have to do that same weighted sum over states, and I'm using the asymptotic probability of being in that state. So this is the cumulative future reward. And what you'll notice is that we don't have the policy anywhere. We just we do have the policy, but it's parameterized by theta. So essentially what we can do is take the gradient of this reward with respect to theta, because that's the signal we're going to use to change or to update theta. We're going to use gradient optimization, presumably using backpropagation in neural networks. So we need to compute this gradient. We want to move in the direction of theta that increases R. We want to move in the direction of theta that increases the total reward. And so if I take the chain rule here, or just basically propagate this derivative through, you'll notice that this term here is a function of theta, and so I compute its gradient with respect to theta. And the next step is really just keeping track of algebra here. So what I've done is I've taken this expression here, and I divide by the policy theta, and so I multiply by the policy pi theta on the left. So these cancel each other out. I'm just dividing by it over here, multiplying it by it over here. So nothing changed. Now I'm asking myself this question, and I hope you're asking the same question. Why didn't my mu sub theta, why didn't I have to chain rule this object here? And that's a really good question. I'm going to have to think about that, and maybe you can comment below in the video, and we can work through kind of what went wrong here. But this is just a sketch of how we can get this policy gradient information. Okay, so you do this, and now you'll notice that this term here is just the gradient of the logarithm of my policy, the gradient of the logarithm. So now we have pi, my policy, times the Q function. So everything to the left here is the reward that I had, times the gradient of the log of the policy with respect to theta. And so now this is the expected value of my quality function times the gradient of the log of my policy with respect to theta. And so this can be used essentially as the signal. This I can compute. So essentially, I can compute the log of my probability pi, and I can weight it by my quality function, and that gives me the information I need to update my weights theta. So I just need to compute this using backpropagation, and this is better conditioned to compute with. Okay, again, this is a bit of a mathematical aside, but if you're interested, for example, in how you actually compute this policy gradient, this is at least one way that you would do that. Okay. Good. So this is where I really wanted to get to is deep Q learning. So most of the most impressive demonstrations of deep reinforcement learning, at least in the last 5 or 10 years, many of them have been deep Q learning, where essentially you learn a quality function with a neural network. So again, we know this is the basic formula for Q learning. It is a off-policy temporal difference learning algorithm. So this is my estimate of my future reward if I'm at state S now and I take action A now. And this is my actual reward. If I take that action and I actually get a reward, this is the actual future reward. And so the error signal between these I can use to update my quality function as I learn through trial and error. So we've already had a whole lecture on this. And so essentially what you can do is you can parameterize this quality function by some neural network weights theta. And this is really, really useful, because if you think about the kinds of things we use Q learning for, or deep Q learning for, the state space S might be astronomically big. For example, if I'm playing a game of backgammon or chess or Go, the number of board combinations in chess is more than 10 to the 80. It's more than there are nucleons in the known universe. And Go has an even larger state space S. So instead of iterating over states over and over, what I'm going to do is I'm going to parameterize this quality function by a much, much lower dimensional set of parameters, theta, and then optimize over theta. So essentially you can think of this as extracting features, kind of low dimensional features of your quality function that are parameterized by theta or some neural network, and we're going to optimize theta to get a better Q function. And this is going to really, really be important to address the curse of dimensionality we have in these very high dimensional state spaces. And so with this one, I actually will write down the actual cost function involved in solving this. So this is the neural network cost function that we use when we build a deep Q learner. Essentially, the loss function that the network is trying to minimize is the expectation of the square of this temporal difference error. So this is literally just the temporal difference signal here, where now my Q functions are parameterized by theta. And so the neural network is going to use, its algorithm, stochastic gradient descent and backpropagation, to optimize these parameters theta to give me the best possible Q function that minimizes this TD error, this temporal difference error. And again, we think that there is a strong evidence that that's what biological learners are doing, at least at some level of their kind of neurological hardware, is minimizing this temporal difference error that we talked about in the last lecture. So this is pretty cool. You can actually just take the update, turn this into a loss function, and the neural network's going to optimize those parameters theta kind of for you. And that's been a very, very powerful approach. So, we've seen this in the DeepMind Atari video game playing. So this is one of my favorite examples of blockout. You've seen this before if you watch my channel, where essentially from this pixel space, a deep Q learner with a convolutional layer can learn the right strategy, the right quality function for what actions to take given what state it finds itself in. And it actually learns some pretty interesting things, that it should actually eventually drill a hole in one side here, and then it'll basically work itself out. And that's the most efficient way to increase its reward, which is really cool. That's why they say human level control, because this algorithm, this deep Q learner, is exploiting the physics of the game to get solutions that only expert humans would find. And so this is the architecture. So it has some convolutional layers, some fully connected layers, from pixel space to joystick, signal. But essentially, this is just a big kind of deep Q learning demonstration, convolutional Q learning. And this is just the list of all of the video games. And I guess, the ones above the line, it is better at or better than human level. And the ones below the line, it's still not as good. Okay, so that was deep Q learning. Essentially, you can have this traditional Q learning, and you can cook up a loss function for your neural network that will essentially, through trial and error, through experience, it will learn the weights theta to give you the best Q function possible. And there's a variation of this that I really like called deep dueling Q networks, or dueling deep Q networks, DDQN, which essentially takes your quality function and it actually splits it into two networks: a value network, which is just a function of the current state, and an advantage network, which says what is the advantage over just the value of being in that state for taking an action A. So this is a good architecture when the difference in quality for different actions is very subtle. So maybe I'm in a really good board position in a game of chess, and the different actions I take are giving me very marginal increases or decreases of my quality function. And so what it does is it splits off the value function of just being in a state from the incremental advantage of taking an action having been in that state. And I mean, this is essentially equivalent to the Q function. It's just another way of writing the Q function. But now you can train two neural networks, and they're kind of dueling with each other. The value function is trying to get as much explanation of that Q function just from the state. And this advantage network A is trying to figure out what the effect of taking actions is. And then you can kind of optimize over these actions and do interesting things. Okay, another really, really important concept in reinforcement learning is the actor-critic learning. And actor-critic methods are actually way older than deep reinforcement learning. So I'm going to tell you what they are in general, and then I'll tell you how we use them for neural networks. So the idea of an actor-critic reinforcement learner is essentially to take the best of both worlds from policy-based and value-based learning. So in a few lectures ago, we talked about policy iteration and value iteration, and they have these kind of different flavors and different benefits and strengths. And so in an actor-critic framework, we're going to have two learners, an actor and a critic. And the actor is basically trying to learn a good policy, and the critic is critiquing that policy based on its estimate of the value. So the critic is learning a value function, essentially, and the actor is learning a policy. Okay, good. So the actor is trying to represent this policy, pi, and the critic is going to be using information from its estimate of the value function. And so one really, really simple way to do this is, remember that policy gradient algorithm I was telling you about? You can essentially do an actor-critic policy gradient, where what you do is you're updating the parameters of your policy. So this is policy update, theta. But you're using the temporal difference signal from your value learner. So your value function is getting updated too. You're trying to learn this value function from your critic. And your critic is essentially giving you the error signal that you use to update your policy. So again, this kind of mixes the best of both worlds. You're using value information, but you're using that to update a policy using this kind of, in some cases, gradient policy information. Now, in the context of deep neural networks, there's some interesting things you can do. One of the ones I like is called this advantage actor-critic network. And it uses that deep dueling queue network I told you before, where you split the quality function into the value function plus the advantage of taking an action. And so essentially now the actor, again, is a deep policy network. So this is a deep neural network for the policy with some weights theta. And then the critic is a deep dueling queue network, Q, that tells you what's the quality of being in a state and taking an action. And so here, similarly, this is that policy iteration, that policy gradient iteration I wrote down earlier, we derived earlier, except now this policy gradient is updating the deep policy network. And gradient iteration is much, much faster than the model-free techniques I was telling you about in the last lecture. Using gradient information will converge way faster than traditional Q-learning or traditional value iteration. But it requires you have a model that's parameterized by theta, that you can take the derivative with respect to theta. But remember, in that deep policy gradient, we needed our quality function. And so this, again, this is an actor-critic network because I'm doing policy iteration, a policy gradient iteration in this case, but I'm using a Q network for that quality function. So my Q network is learning the quality function, and I'm updating my policy using this policy gradient network. And presumably, you update your DDQN the way you always do. By once you take actions and you get rewards, you'll update this Q function using the temporal difference error. So I think this is really cool. You can kind of mix the best of a value-based formulation, and really Q networks are kind of value-based, and policy-based for the optimization. So you optimize the policy using value-based information. So this is really cool. And this is different than Q-learning, which is purely value-based. So in Q-learning, you are still updating the Q function, but you're updating the Q function based on Q information, and then at the end of each optimization, then you figure out what your best policy is just by reading it off. Whereas here, you're kind of jointly, you're optimizing the policy directly, but using this Q information, this value-based information. So this is kind of a neat approach. Okay, so that, again, was just the tip of the iceberg of deep reinforcement learning, but we got a little bit more specific into some of these methods. So very, very popular deep quality function networks. You can use those to do deep policy gradients, for example, in an actor-critic. So if you like, there is an actor-critic method that uses a deep Q network for the critic to do a deep policy gradient optimization. Now you'll notice conspicuously here there is this deep model predictive control block that I didn't really talk at all about. It's kind of a different flavor of optimization, and I'm almost certainly going to have a whole video or series on deep model predictive control later. But there's some really interesting work in the community where people are learning these kind of really good optimal nonlinear controllers using these classic dynamical systems optimizations like model predictive control. But then they try to learn a policy that mimics that model predictive controller. So this can be a very expensive online optimization. It requires a lot of model forecasting. It's very, very computationally intensive typically. And so if I do that expensive computation, maybe I'm teaching a quadrotor how to fly through an obstacle field, Once I learn the right control actions, maybe I can embed that in a neural network. Maybe I can train a policy that very rapidly kind of encodes the information of these deep model predictive controllers. Okay, so that was, again, just a very high-level overview of some really important topics building on some of the pieces that we've been learning over the last few lectures. All right, thank you.